When the charge distribution is highly symmetric, Gauss's law is useful for evaluating the electric fields. In choosing the surface, we always take advantage of the symmetry of the charge distribution so that E can be removed from the integral sign. Please look at this figure. Here is an insulating solid sphere with a radius A, which has a uniform volume charge density ρ and carries a total positive charge Q. Please find the electric field in space. Firstly, we shall analyze the symmetry of the electric field due to this charge distribution to see if Gauss's law could be employed to calculate the electric field. Since the charge is distributed uniformly throughout the sphere, the charge distribution has a spherical symmetry. So the electric field must have a spherical symmetry, which means that the electric field is directed radially and the magnitude of the electric field is equivalent everywhere on the spherical surface concentric with the sphere. Therefore, this spherical surface could be chosen as the Gaussian surface. Since we have two regions in space, the electric fields both inside and outside of the sphere will be evaluated. For points outside the sphere, a spherical Gaussian surface with a radius r larger than a is chosen. For this choice, the electric field everywhere on the surface is parallel to dA, so E.dA reduces to EdA. By symmetry, E has the same value everywhere on the surface, so we can remove E from the integral sign. We solve for E, and it's expressed by this equation. This field is identical to that of a point charge. The electric field due to a uniformly charged sphere in the region outside the sphere is equivalent to that of a point charge located at the center of the sphere. For points inside the sphere, a spherical Gaussian surface with a radius r smaller than a is chosen. We need to find the net charge inside the Gaussian surface Qin. Qin equals rho delta V, and delta V is the volume of the region enclosed by the Gaussian surface. By applying Gauss's law, we could solve for E. From these results, we can find the electric field inside the sphere is different from the one outside the sphere. When R approaches 0, E approaches 0. Here shows a plot of E versus R for a uniformly charged insulating sphere. The electric field inside the sphere varies linearly with R. The field outside the sphere is the same as that of a point charge Q located at the center. Further, we found that the value of the field is the same as the surface is approached from both directions. That means the magnitude of the field is continuous. Let me give you a second example. Here is a uniformly charged line with an infinite length. Please find the electric field a distance r from the line. Let's first analyze the symmetry of the electric field in this case. Because the charge is distributed uniformly along the line with an infinite length, the charge distribution has cylindrical symmetry, and we can apply Gauss's law to find the electric field. Let's see the magnitude of the field. Since the line of the charge is infinitely long, the field is the same at all points which have the equivalent distance from the line, regardless of the vertical position. Then how about the direction of the electric field? The symmetry of the charge distribution establishes E perpendicular to the line charge and directed outward since the line charge is positive. In this case, how to choose a Gaussian surface? Since the electric field is cylindrically symmetric, we shall choose a cylindrical Gaussian surface of a radius r and a length l that is coaxial with the line charge. The end view gives us a clear picture showing that the electric field is constant in the magnitude and perpendicular to the curved surface everywhere. The field is parallel to the two ends of the cylinder, and the flux through these two ends is 0. By applying Gauss's law, we have this expression, noting that the total charge inside the Gaussian surface is lambda L. We substitute the area 2 pi r L of the curved surface and solve for the magnitude of the electric field. This result shows that the electric field due to a cylindrically symmetric charge distribution varies as 1 over r. One more example here. Here is an infinite plane carrying the positive charge. The uniform surface charge density is sigma. Find the electric field in space. In this case, the charge is distributed uniformly over the plane and the charge distribution is symmetric. Therefore, Gauss's law can be used to calculate the electric field. Since the plane of the charge is infinitely large, the electric field should be the same at all points equidistant from the plane. By symmetry of the situation, E must be perpendicular to the plane at all points. The direction of E is away from the plane since the plane carries positive charges. The direction of E on one side of the plane must be opposite to its direction on the other side. So, we shall choose a small cylinder as a Gaussian surface, as shown in this figure. The axis of the cylinder is perpendicular to the plane, and each flat surface has an area A. The two ends are equidistant from the plane. We found that the electric field is parallel to the curved surface of the cylinder, and therefore the flux through the curved surface is 0. For the ends of the cylinder, E is parallel to dA, so the flux through each end of the cylinder is EA, and the total flux through the entire Gaussian surface is just that through the ends. By applying Gauss's law, we have this expression, noting that the net charge enclosed by the Gaussian surface is sigma A. We solve for E. We found that it doesn't depend on r, suggesting the field is uniform everywhere in space. Above examples showed us the evaluation of the symmetric electric field by applying Gauss's law. Before ending this lecture, I have a question. Is Gauss's law only valid for the symmetric electric field? Please think about it. Okay, see you next lecture.